The neutral current for a single-phase feeder can be calculated based on the National Electrical Code. Table 310.15b16 provides guidance for calculating the neutral current, abbreviated as IN. The formula is N equals the quantity of the maximum unbalanced load plus the neutral current from branch circuits divided by 2. In a scenario with a maximum unbalanced load of 0 amps and no neutral current from branch circuits, the resulting neutral current would be 0 amps. However, Table 310.16 mandates that the neutral conductor possess an ampacity of at least 50% of the feeder ampacity. Given a 200 amp service, this means the neutral conductor must have an ampacity of at least 100 amps. A number 1 conductor, possessing an ampacity of 115 amps according to the NEC ampacity tables for copper conductors, would be sufficient in this case. This assumes the conductor is insulated with a rating of 75 degrees Celsius and installed in a typical environment. The grounding electrode conductor, often abbreviated as GEC, is a critical component of the electrical system responsible for connecting the service equipment to the grounding electrode. The grounding electrode system may consist of a ground rod, a ground ring, a metallic water pipe, or other approved grounding electrodes. It is essential for providing a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices like circuit breakers and fuses. This ensures that in the event of a ground fault, the fault current will quickly trip the breaker or blow the fuse, minimizing the risk of electrical shock and fire. The size of the grounding electrode conductor is determined by the size of the service entrance conductors, and it is crucial to adhere to the requirements outlined in the National Electrical Code. Table 250.66 is a primary reference for determining the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. For a 200 amp service, NEC Table 250.66 dictates the minimum size of the grounding electrode conductor when connected to a ground rod, ground plate, or other electrodes. For a 200 amp service, the minimum size of the copper grounding electrode conductor is number 6 if connected to a rod, pipe, or plate electrode. However, if connected to a concrete encased electrode or ground ring, the minimum size is number 2. The grounding electrode conductor must be run to the grounding electrode. The grounding electrode itself can be a ground rod, a metallic water pipe, or a concrete encased electrode. The connection to the grounding electrode must be made with approved methods, such as exothermic welding or listed connectors. It is important to ensure that the grounding electrode conductor is protected from physical damage. If the conductor is exposed to physical damage, it should be installed in conduit or otherwise protected. The path from the service equipment to the grounding electrode should be as short and direct as possible. This helps to minimize impedance and ensure that the grounding system functions effectively. The purpose of the grounding electrode conductor is to provide a low impedance path for fault current to return to the source. This allows overcurrent protection devices to quickly trip and clear the fault, protecting people and equipment. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. For a 200 amp service, the minimum size of the grounding electrode conductor is number 6 copper if connected to a rod, pipe, or plate electrode. If connected to a concrete encased electrode or ground ring, the minimum size is number 2 copper. The grounding electrode conductor must be run to the grounding electrode, which can be a ground rod, a metallic water pipe, or a concrete encased electrode. The connection to the grounding electrode must be made with approved methods. The grounding electrode conductor should be protected from physical damage and installed in a short and direct path. Understanding the requirements for neutral and grounding electrode conductors is crucial for ensuring electrical safety in compliance with the National Electrical Code. These conductors play essential roles in protecting people and equipment from electrical hazards. Properly sized and installed neutral conductors ensure that unbalanced currents can be safely carried back to the source, while grounding electrode conductors provide a low impedance path for fault currents, enabling overcurrent protection devices to quickly clear faults. The National Electrical Code, or NEC, provides comprehensive guidelines for electrical installations, including requirements for conductor sizing, installation methods, and safety practices. Adhering to the NEC is essential for ensuring that electrical systems are safe and reliable. In addition to the NEC, local electrical codes and regulations may also apply. It is important to consult with local authorities to determine the specific requirements in your area. A qualified electrician should perform all electrical work. Electrical work can be dangerous, and it is important to have the necessary knowledge and skills to perform the work safely. Working with electricity requires a thorough understanding of electrical principles, safety procedures, and the applicable codes and regulations. A qualified electrician has the training and experience to perform electrical work safely and correctly. They can also help ensure that the electrical system complies with all applicable codes and regulations. When selecting an electrician, it is important to choose one who is licensed and insured. A licensed electrician has met the requirements established by the state or local jurisdiction to perform electrical work. Insurance protects you from liability in the event of an accident or injury. It is also important to check the electrician's references and reviews. This can give you an idea of the quality of their work and their customer service. Before hiring an electrician, be sure to get a written estimate of the cost of the work. The estimate should include a detailed breakdown of the materials and labor costs. It is also important to ask the electrician about their warranty policy. A good warranty will protect you from defects in workmanship or materials. When working with electricity, it is important to follow all safety precautions. Always turn off the power before working on any electrical equipment. Use insulated tools and wear appropriate personal protective equipment, such as safety glasses and gloves. Never work on electrical equipment in wet or damp conditions. If you are not comfortable working with electricity, it is best to hire a qualified electrician. Attempting to perform electrical work without the necessary knowledge and skills can be dangerous and may result in serious injury or even death. The neutral conductor plays a critical role in an electrical system by providing a return path for unbalanced currents. In a balanced three-phase system, the currents in each phase cancel each other out, and there is no current flowing in the neutral conductor. However, in most real-world scenarios, the loads on each phase are not perfectly balanced, resulting in an unbalanced current that flows in the neutral conductor. The neutral conductor must be sized to carry this unbalanced current safely. The National Electrical Code provides guidelines for determining the minimum size of the neutral conductor. Table 310.15b16 is a key reference for calculating the neutral load. The formula provided accounts for the maximum unbalanced load in any neutral current from branch circuits. It is important to accurately assess the expected unbalanced load to ensure that the neutral conductor is adequately sized. If the neutral conductor is undersized, it can overheat and create a fire hazard. The grounding electrode conductor, or GEC, provides a path for fault current to return to the source. This allows overcurrent protection devices, such as circuit breakers and fuses, to quickly trip and clear the fault, protecting people and equipment from electrical shock and fire. The GEC connects the service equipment to the grounding electrode, which is typically a ground rod, a metallic water pipe, or a concrete encased electrode. The size of the GEC is determined by the size of the service entrance conductors, as specified in NEC Table 250.66. It is crucial to use the correct size GEC to ensure that it can effectively carry fault current. If the GEC is undersized, it may not be able to handle the fault current, which can result in a dangerous voltage on the grounded metal parts of the electrical system. The grounding electrode system should be installed in accordance with the requirements of the National Electrical Code. The grounding electrode should be located as close as possible to the service equipment and should be accessible for inspection and testing. The connection between the GEC and the grounding electrode should be made with approved methods, such as exothermic welding or listed connectors. Regular inspection and testing of the grounding electrode system is recommended to ensure that it is functioning properly. The resistance of the grounding electrode system should be measured periodically to verify that it is within acceptable limits. If the resistance is too high, It may indicate a problem with the grounding electrode or the connection between the GEC and the grounding electrode. The National Electrical Code is a comprehensive set of standards for electrical installations. It is updated every 3 years to reflect the latest advances in electrical technology and safety practices. It is essential for electricians, electrical engineers, and other professionals involved in electrical work to stay up to date with the latest edition of the NEC. The NEC covers a wide range of topics, including conductor sizing, overcurrent protection, grounding, wiring methods, and equipment installation. It also includes requirements for special occupancies, such as hazardous locations, healthcare facilities, and data centers. Adherence to the NEC is essential for ensuring the safety and reliability of electrical systems. Local electrical codes and regulations may also apply, and it is important to consult with local authorities to determine the specific requirements in your area. Proper conductor sizing is crucial for the safe and efficient operation of electrical systems. Undersized conductors can overheat and create a fire hazard, while oversized conductors can be unnecessarily expensive. The National Electrical Code provides detailed guidelines for conductor sizing, taking into account factors such as the ampacity of the conductor, the ambient temperature, the number of conductors in a raceway, and the type of load being served. The ampacity of a conductor is the maximum amount of current that it can carry safely without exceeding its temperature rating. The ampacity of a conductor is determined by its size, material, and insulation type. NEC Table 310.15 provides ampacity ratings for various types of conductors. The ambient temperature is the temperature of the surrounding environment. The ampacity of a conductor must be derated if the ambient temperature is higher than the temperature rating of the conductor's insulation. The number of conductors in a raceway also affects the ampacity of the conductors. If there are more than 3 current-carrying conductors in a raceway, the ampacity of the conductors must be derated. The type of load being served also affects the conductor sizing. For example, conductors serving motor loads must be sized larger than conductors serving lighting loads. In addition to the NEC, there are other resources available to help with conductor sizing, such as software programs and online calculators. These tools can simplify the process of conductor sizing and help ensure that the conductors are properly sized for the application. Overcurrent protection is another essential aspect of electrical safety. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect conductors and equipment from damage caused by excessive current. Circuit breakers are automatic switches that trip and interrupt the flow of current when an overcurrent condition occurs. Fuses are one-time devices that melt and interrupt the flow of current when an overcurrent condition occurs. The size of the overcurrent protection device must be carefully selected to protect the conductors and equipment that it serves. The overcurrent protection device should be sized no larger than the ampacity of the conductors that it protects. The National Electrical Code provides detailed requirements for overcurrent protection. Article 240 of the NEC covers overcurrent protection in detail. It is important to understand these requirements to ensure that the electrical system is properly protected from overcurrent conditions. Grounding is another essential aspect of electrical safety. Grounding provides a low impedance path for fault current to return to the source, which allows overcurrent protection devices to quickly trip and clear the fault. Grounding also helps to reduce the risk of electric shock by limiting the voltage on grounded metal parts of the electrical system. The National Electrical Code provides detailed requirements for grounding. Article 250 of the NEC covers grounding in detail. It is important to understand these requirements to ensure that the electrical system is properly grounded. Wiring methods are the techniques and materials used to install electrical wiring. The National Electrical Code provides detailed requirements for wiring methods. Chapter 3 of the NEC covers wiring methods in detail. It is important to use approved wiring methods and to follow the requirements of the NEC to ensure that the electrical wiring is installed safely and correctly. Equipment installation is another important aspect of electrical safety. The National Electrical Code provides detailed requirements for the installation of electrical equipment. Chapter 4 of the NEC covers equipment for general use. It is important to follow the requirements of the NEC to ensure that electrical equipment is installed safely and correctly. Special occupancies, such as hazardous locations, healthcare facilities, and data centers, have unique electrical requirements. The National Electrical Code provides special requirements for these occupancies. Chapters 5, 6, and 7 of the NEC cover special occupancies in detail. It is important to understand these requirements to ensure that the electrical systems in these occupancies are safe and reliable. The proper sizing and installation of neutral and grounding electrode conductors are essential for electrical safety. The National Electrical Code provides detailed guidelines for these conductors, and it is important to follow these guidelines to ensure that the electrical system is safe and reliable. Regular inspection and testing of the electrical system are also recommended to ensure that it is functioning properly. If you have any questions or concerns about electrical safety, it is best to consult with a qualified electrician.